Hi everyone, today, we're diving into one of the most foundational results in computational complexity theory, Cook's theorem, from Stephen Cook's 1971 paper. This result formally established the concept of NP completeness, starting with SAT. Let's break it down together. First, let's ask, what are NP problems? These are decision problems where, if the answer is yes, you can verify the solution in polynomial time using a non-deterministic Turing machine, or NTM for short. But how do you show that one problem, like SAT, is complete for NP? Cook's theorem says that the Boolean satisfiability problem, or SAT, is NP complete. What does this mean? It means two things. 1. SAT is in NP, it's easy to verify a solution. 2. Every other NP problem can be reduced to SAT in polynomial time. This second part is what makes it NP complete. It's a hardest problem in NP. Cook's proof is elegant. It shows how to take any NP problem and encode its computation, step by step, as a SAT formula. Let's walk through the construction. The SAT formula W encodes the behavior of a non-deterministic Turing machine, or NTM, M, as it processes an input W. The goal is to ensure that a W is satisfiable if and only if the NTM M accepts W. Let's break this down step by step. 1. Initial configuration. First, we set the stage. At time t equals 0. The NTM starts in its initial state, q_0. The tape contains the input W, written in consecutive cells starting from position 0. The head of the NTM is at the first position of the tape. The formula enforces this using variables. X, 0, 0, q_0. This says that at time t equals 0, the machine is in state q_0 and the head is at position 0. Y, 0, I, a_I. This specifies that each tape position I holds the symbol a_I, corresponding to the characters of W. Here's how we write this as a formula. 2. Transition rules. Next, we encode the machine's movement as it processes the tape. These are the transition rules, which ensure at each time step t, the machine follows its transition function correctly. This includes updating the state, modifying the tape, and moving the head. For example, if the NTM is in state S, reads symbol A, and the transition function tells it to write B, move right, and switch to state S, the formula encodes this behavior. This step ensures that the computation is consistent with the NTM's design. 3. Consistency. Consistency is critical. It ensures that the encoding doesn't break the rules of logic. For instance, a tape cell can only hold one symbol at a time. The machine can only be in one state at any time step. These constraints make sure the computation is well defined at every step. 4. Halting condition. Now comes the halting condition, the moment we care about most, acceptance. This part ensures that the formula is satisfiable only if the NTM halts in an accepting state, which means there's some time t in head position I where the machine reaches the state q_accept. 5. Time bound. Finally, we restrict the computation to a polynomial number of steps. If the input W is length n, the machine only runs for t, n, steps, where t is a polynomial. Any variables for time steps beyond t, n, are irrelevant. The full formula. When you put all these components together, the SAT formula A, W, looks like this. This formula is satisfiable if and only if the NTM accepts W. And that's the beauty of Cook's construction, it transforms the abstract computation of an NTM into a concrete SAT problem. This formula is satisfiable if and only if the NTM accepts W. By doing this, Cook showed that any NP problem could be transformed into SAT. This discovery opened the door to understanding NP completeness and proved that SAT is the universal language for hard problems in NP. Today, Cook's theorem underpins so much of computer science. SAT solvers are used in areas like AI, logistics, and even hardware design. And the idea of NP completeness helps us recognize when problems might not have efficient solutions. So that's the essence of Cook's theorem, a groundbreaking result that continues to shape how we approach computational problems today. If you enjoyed this breakdown, make sure to like and subscribe for more deep dives into computer science. Thanks for watching.